The moon we see every night is an illusion of constancy. Because it is tidally locked to our planet, it keeps one face permanently turned toward us, showing the other side only via a tiny fraction of orbital wobble. The far side remained completely hidden from human sight until the space age, a completely separate geological realm that contains clues to the ancient history of the entire solar system. Hidden beneath its battered, cratered surface is a record stretching back more than 4 billion years, containing evidence that is forcing scientists to fundamentally rewrite the origin story of our world. Every night, humanity participates in an unspoken optical illusion. We look up at the silver orb suspended in the night sky and mistake familiarity for completeness. We watch it grow from a thin, fragile crescent into a radiant circle, tracking its movements across the seasons, noticing the dark stains spilled across its surface and the brilliant, chaotic splash of its craters. Yet, every generation of humans that has ever walked the Earth has looked upon the exact same landscape. We are locked in a cosmic gaze with a companion that refuses to turn its head. Because of a precise geometric arrangement, the moon conceals an entire hemisphere from our planet, revealing only a tiny fraction of its secrets, roughly 59% if you account for the subtle orbital wobble known as libration. Beyond that edge lies a domain entirely cut off from our view, a place that remained completely unseen until the dawn of the space age. This hidden half is not merely the reverse side of a familiar object. Geologically, chemically, and structurally, the lunar far side is a completely different world. For 4 billion years, while the near side was being flooded by dark volcanic plains, the far side sat in the freezing dark, quietly recording the violent infancy of our solar system. Embedded within its deep, pulverized soil are the structural keys to understanding how planetary bodies form, cool, and differentiate. For half a century, space exploration was defined by a geochemical monopoly, with every single piece of rock brought back to Earth coming from the visible face. But in recent years, a series of robotic missions culminating in an extraordinary engineering feat in 2024 has finally breached this wall of architectural ignorance. The gray dirt gathered from the moon's hidden face is doing something far more radical than expanding our maps. It is forcing planetary scientists to completely dismantle and rewrite the origin story of our entire planet. To comprehend the scale of what has been discovered, one must first look at the mechanism that kept this hemisphere hidden for eons. The fact that the moon rotates on its axis at the exact same speed that it circles the Earth is not an astronomical fluke, nor is it a permanent condition of the cosmos. It is the inescapable final chapter in a long, brutal, gravitational relationship. Billions of years ago, when the moon was much closer to a young, molten Earth, it spun rapidly on its own independent axis. But the moon is not a perfect geometric sphere. It is slightly elongated, possessing a subtle structural bulge pulled out by the Earth's immense mass. As the moon rotated through this gravitational field, the Earth's gravity tugged continuously on this asymmetric bulge. This relentless pulling acted as a cosmic brake, generating internal friction that slowly bled away the moon's rotational momentum. Over hundreds of millions of years, the moon's independent spin slowed down until its rotation matched its orbital period precisely. This state of tidal locking was achieved billions of years ago. Since that moment, the moon has moved around us like a dancer who never breaks eye contact, ensuring its hidden face remains pointed toward the deep void of space. For millennia, this arrangement limited human imagination. When early telescopes were pointed at the visible face, astronomers noticed vast, dark patches tracking across the surface. They called these regions Maria, the Latin word for seas, believing they were looking at massive oceans of liquid water. Today, we know these features are actually immense, flat plains of ancient basaltic lava that filled in massive impact basins. These dark plains, contrasted against the blindingly bright cratered highlands, formed the face that humanity came to know. The baseline assumption among scientists was simple. If we could somehow step around to the other side, we would see a mirrored landscape, a similar distribution of dark volcanic seas and rugged white highlands. That assumption evaporated on October 7, 1959. The Soviet probe Luna 3 looped behind the Moon, fighting the extreme constraints of early space technology to snap the first photographs of the hidden hemisphere. The images that beamed back to Earth were grainy, heavily distorted smudges of gray, but they sent a profound shockwave through the scientific community. The expected symmetry was completely absent. The dark, sprawling maria that cover nearly 1/3 of the near side were almost entirely missing from the far side. Instead, the hidden face revealed an almost unbroken, blindingly bright expanse of heavily battered highlands. It was a landscape saturated with impact scars, where ancient craters were stacked on top of older craters in a chaotic, endless patchwork of violence. This dramatic structural discrepancy between the two halves of the same satellite is known as the lunar dichotomy. It remains one of the most stubborn and fascinating puzzles in planetary science. If the Moon was born from a single cataclysmic event, how could its two halves look so radically different? The leading consensus on the birth of the Moon suggests that roughly 4.5 billion years ago, a protoplanet the size of Mars, named Theia, collided with the proto-Earth. The sheer kinetic energy of the impact vaporized both the intruder and a massive portion of the Earth's early crust, launching a ringside disk of superheated debris into orbit. Over a remarkably short period, this molten ring coalesced to form the Moon. Because it was born from a singular debris disk, orbiting a single planet, and subjected to the exact same external bombardment of asteroids, the stark divergence between its hemispheres implies that internal or localized mechanisms altered its evolution after its birth. For decades, testing any theory regarding the lunar dichotomy was impossible due to a fundamental physical barrier. The Moon is a colossal shield of solid rock over 3,400 kilometers thick. This massive bulk completely blocks high-frequency radio signals. If you drop a spacecraft onto the far side, its line-of-sight communication with tracking stations on Earth goes dead instantly. During the historic Apollo missions of the late 1960s and 1970s, astronauts drifted over the far side in their command modules, looking down at the rugged, bright terrain with their own eyes. They marveled at its desolation, noting the complete lack of the dark volcanic plains they had used as navigation landmarks on the near side. But they could only look. Landing a crew, or even a simple robotic probe, required solving the communication blackout, a technological hurdle that no space agency attempted for the first 60 years of the space age. The 382 kilograms of lunar material brought home by the Apollo missions, along with the automated samples retrieved by the Soviet Union's Luna program, all came from a narrow, geographically restricted band on the near side. The silence was broken by an ambitious, multi-stage exploration strategy executed by the Chinese National Space Administration. The critical breakthrough was not a lander, but an orbital bridge. In June 2018, China launched a dedicated communications satellite named Kakao, meaning Magpie Bridge. They sent this satellite to a specific gravitational parking spot known as the Earth-Moon Lagrange Point 2, or L2, situated roughly 65,000 kilometers beyond the far side of the Moon. At this precise location, the combined gravitational pull of the Earth and the Moon allows a spacecraft to hover in a stable halo orbit, maintaining a permanent, unobstructed line of sight to both the hidden face of the Moon and the tracking dishes on Earth. With the communication bridge securely established, the far side was suddenly accessible. On January 3, 2019, the Chang'e 4 spacecraft split the silence of the hidden hemisphere, executing the first-ever soft landing on the far side. It targeted a highly specific and scientifically revered location, the Von Karman crater. This 186-kilometer-wide depression does not sit on ordinary terrain. It is located deep within the floor of the South Pole-Aitken basin. The South Pole-Aitken basin, or SPA, is a monumental feature that dominates the lower half of the far side map. stretching approximately 500 kilometers from edge to edge and plunging between 6 and 8 kilometers deep. It ranks as one of the largest and oldest confirmed impact structures in the entire solar system. To put its size into perspective, the basin would cover nearly 70% of the distance between New York and Las Vegas. It is an ancient continental-scale wound inflicted on the Moon roughly 4.2 to 4.3 billion years ago, within the first few hundred million years of its existence. When the colossal asteroid that formed the SPA basin struck, it did not merely leave a superficial dent. The impact was so energetic that it completely excavated the Moon's primary crust, punching straight through to the underlying mantle. For planetary geologists, the floor of the SPA basin is the ultimate holy grail. Because the crust was stripped away billions of years ago, the basin floor is theoretically littered with exposed material from the Moon's deep interior rocks that crystallized when the Moon was a churning ball of liquid magma. By landing inside Von Karman crater, Chang'e 4 was positioned to touch the primitive interior of the Moon. Deployed from the lander, a small 140-kilogram rover named Yutu-2, or Jade Rabbit 2, began moving across the powdery gray soil. Equipped with a visible and near-infrared spectrometer, the rover quickly made a discovery that sent ripples through the international scientific community. As it scanned the regolith of the crater floor, its instruments detected clear chemical signatures of low-calcium pyroxene and olivine. These are dense, magnesium and iron-rich minerals that are largely absent from the light, aluminum-rich rocks of the upper crust, but are the primary building blocks of the planetary mantle. The finding provided the first direct, on-the-ground validation of long-standing planetary models. The ancient impact had indeed hauled the deep interior of the Moon to the surface, where it had sat undisturbed for over 4 billion years. However, the discovery was wrapped in scientific nuance. The signatures of these mantle minerals were not found in pristine, uniform boulders, but were thoroughly chewed up and mixed into the fine lunar dust by billions of years of subsequent micrometeorite impacts. Some international researchers urged a degree of analytical caution, noting that while the spectroscopic data strongly pointed toward mantle-derived rock, it could also indicate unusual, deep crustal volcanic compositions that had been churned up from shallower depths. As Yutu-2 continued its slow journey, navigating deep temperature swings that plunged to -180 degrees Celsius during the 2-week-long lunar nights, its ground-penetrating radar peered 40 meters into the subterranean dark. The radar images revealed a complex, vertical textbook of lunar history, distinct, alternating layers of fine regolith, coarse impact ejecta from distant cratering events, and ancient, buried lava flows. This complex stratigraphy proved that the far side, despite its lack of massive superficial seas, possessed a rich and localized volcanic history of its own. In July 2019, the rover came across another anomaly inside a fresh, small impact crater. Controllers on Earth noticed a localized patch of material that exhibited an unusual, dark sheen, completely distinct from the matte gray dust surrounding it. Early field descriptions from the mission team calling it a gel-like substance sparked widespread curiosity, but careful spectroscopic analysis eventually revealed a fascinating truth. The material was impact glass, a mass of lunar rock that had been instantly flash-melted by the extreme heat of a meteorite strike and rapidly cooled into a dark green, glassy solid. Impact glass is a natural chemical time capsule. The sudden melting and quenching process seals in the volatile elements and structural composition of the target rock at the exact microsecond of the collision. While Yutu-2's in situ measurements were revolutionary, automated rovers are fundamentally constrained by the size and sensitivity of the instruments they can carry across the lunar terrain. To definitively resolve the nature of the far side, scientists needed to hold these rocks in their hands. They required the massive, highly specialized instruments found only in terrestrial laboratories, secondary ion mass spectrometers, cleanrooms, and ultra-precise radiometric dating systems. Before attempting to fly a sample return is an open, dynamic system that interacts directly with external cosmic bombardment. A world that appears geologically dead from an internal thermal perspective can be locally reanimated by the immense kinetic energy of a well-placed impactor. This realization suggests that the internal structural histories of other small, ancient bodies across the solar system, such as the asteroid Vesta or the moons of Mars, cannot be reliably modeled using a single global cooling curve. They must instead be analyzed as a complex patchwork of localized thermal events dictated by the chaotic, random chronology of impact cratering. The physical state and placement of the volatile compounds trapped within the microscopic inclusions of the minerals are also providing the first unedited look at the chemical composition of the ancient impactors themselves. By utilizing mass spectrometry to analyze the precise isotopic ratios of hydrogen and nitrogen within tiny glass pockets sealed inside olivine crystals, scientists can identify the exact origins of the water that seeded the Earth-Moon system. If the trapped moisture exhibits a high deuterium to hydrogen ratio, it matches the unmistakable chemical fingerprint of primitive comets originating from the freezing outer peripheries of the solar system. If the ratio is significantly lower, it aligns perfectly with the carbonaceous chondrite asteroids that formed within the warmer, inner regions of the early protoplanetary disk. The initial readings from the far side material point toward a heavy predominance of asteroid-like volatile signatures. This indicates that the delivery of life-supporting volatile compounds to the early Earth and Moon was not a late, sudden addition brought by a spectacular deluge of icy comets, but was an ongoing, intrinsic process that occurred during the primary accretion phase of the inner planets. This role as a pristine environmental archive highlights the unique value of the lunar far side. Because the Moon lacks an atmosphere, a global magnetic field, and a hydrological cycle, its surface is directly exposed to the unmitigated output of the space environment. Every energetic particle emitted by the Sun, every cosmic ray originating from distant galactic supernovae, and every grain of high-velocity interplanetary dust that crosses the Moon's orbital path collides directly with the surface regolith. The far side is uniquely suited to preserving this space weather record. The near side of the Moon is periodically shielded from the solar wind when its monthly orbit carries it through the long, streaming magnetic tail of the Earth's magnetosphere. For several days each month, the visible face sits inside this protective magnetic bubble, shielded from solar particles but continuously bombarded instead by the terrestrial ions that leak outward from our planet's upper atmosphere, a phenomenon known as Earth wind. The far side receives no such terrestrial contamination and enjoys no magnetic protection. For over 4 billion years, it has been continuously bathed in the pure, unfiltered output of our star. As a direct result of this unshielded exposure, solar wind ions, predominantly hydrogen, helium, carbon, and nitrogen, are implanted directly into the outer few nanometers of the far side soil grains. By carefully peeling back these outer crystalline layers using precise ion beam etching techniques in the laboratory, scientists can read the historical output of the Sun like growth rings in an ancient forest. The concentration and isotopic depth profiles of helium and solar hydrogen within the regolith provide a physical record of our star's behavioral evolution stretching back to its volatile youth. This allows astrophysicists to reconstruct the luminosity and flare activity of the ancient Sun during the critical, vulnerable epoch when life was first attempting to organize itself within the early oceans of the Earth. The operational success of these robotic voyages has also driven an evolutionary leap in the infrastructure of deep space navigation. Operating a complex sample return mission on a world where direct line-of-sight communication is physically impossible requires moving past the simple tracking mechanics of the 20th century. The deployment of relay satellites into stable, frozen elliptical orbits demonstrated a masterful understanding of orbital mechanics. A halo orbit around the balance point behind the Moon is an unstable gravitational ridge. A spacecraft placed there is constantly subjected to gravitational perturbations from the Earth, Moon, and Sun. Maintaining this delicate orbital choreography requires constant, autonomous microthruster firings to prevent the satellite from falling off the ridge and drifting away into interplanetary space. Managing this orbital balancing act while simultaneously routing a high-bandwidth multi-channel data stream through thousands of kilometers of solid rock requires a level of automated ground tracking and autonomous machine navigation that was pure science fiction during the Apollo era. The autonomous landing of the probe inside the crater was a historic milestone for machine vision and real-time algorithmic decision-making. During near-side landings, automated systems can rely on immediate tracking data from Earth-based arrays to assist in path correction. On the far side, the lander is entirely on its own during the critical 15-minute descent window. The spacecraft's computer must independently process high-resolution optical data and laser altimetry streams within milliseconds, mapping the incoming terrain, calculating slope angles, identifying hazardous boulder fields, and commanding immediate trajectory shifts while plummeting toward the airless surface. The gray dust kicked up by the lander's braking rocket settled onto a landscape that had not experienced a significant mechanical disturbance for hundreds of millions of years, outside the occasional ticking clock of a distant meteorite impact. The geopolitical and strategic drivers behind these missions cannot be separated from their scientific achievements. The intense focus directed at the lunar South Pole and the surrounding far-side basins by modern space agencies is fueled by a combination of unique geographical traits and vital resource potential. Because of the Moon's extremely low axial tilt, just 1.5 degrees, the Sun crawls along the horizon at the lunar poles, casting immense, eternal shadows inside deep impact craters. These permanently shadowed regions are completely cut off from solar radiation. Hovering just a few degrees above absolute zero, they rank among the coldest environments in the known universe, acting as highly efficient cryogenic traps that have captured and frozen volatile compounds delivered by comets over geological timescales. Orbiting satellites equipped with instruments have mapped significant signatures of hydrogen concentrated within these dark polar zones, confirming the presence of vast reserves of water ice mixed directly into the frozen regolith. For a spacefaring species, water ice on the Moon is not merely an asset for life support, it is the definitive foundation of a sustainable space economy. By utilizing solar power arrays situated on permanently illuminated crater rims to drive electrolysis systems, future outposts can split this harvested ice into its constituent components, pure hydrogen and oxygen. This is the exact chemical recipe for high-energy rocket propellant. Because the Moon's gravity is only 1/6 that of Earth's, launching a vehicle from the lunar face requires a tiny fraction of the escape velocity needed to break free from Earth's deep gravitational well. Constructing a lunar refueling infrastructure would effectively transform our satellite into a low-gravity stepping stone for the rest of the solar system, slashing the cost, mass requirements, and structural complexity of long-duration missions targeting Mars, the asteroid belt, and deep space. Beyond these tangible resources, the far side of the Moon offers an invaluable, intangible asset that exists nowhere else in our region of space: absolute electromagnetic isolation. The Earth is an incredibly noisy neighbor, wrapped in a dense, blinding fog of human-made radio frequency interference generated by global communications networks, cellular infrastructure, military radar systems, and industrial machinery. This electromagnetic pollution leaks constantly into the orbital environment, blinding our terrestrial radio telescopes and severely limiting our ability to detect the incredibly faint, ancient radio signatures traveling from the furthest reaches of space-time. The far side of the Moon is the only location within human reach that is entirely shielded from this human-made din. The bulk of the Moon acts as a natural thousands of kilometers barrier of solid rock, creating a pristine radio shadow that blocks out 100% of terrestrial radio interference. Establishing a low-frequency radio telescope array across the ancient, stable highlands of the far side would grant astronomers unprecedented access to the cosmic dark ages, the mysterious, unmapped epoch of universal history before the first generation of stars ignited. During this formative era, the universe was filled solely with a cooling, expanding fog of neutral hydrogen gas. This neutral hydrogen emitted a subtle, highly specific wavelength of light known to physics as the 21-centimeter line. Over 13 billion years of cosmic expansion, this primordial signal has been stretched into long, low-frequency radio waves. These ancient waves are physically incapable of penetrating the Earth's ionosphere and are completely obliterated by human radio noise on the near side. Capturing this pristine cosmological footprint from the quiet solitude of the far side would allow cosmologists to directly map the distribution of dark matter and regular matter in the infant universe, providing an unedited view of the literal birth of the first stellar structures and galaxies. As the global scientific community continues to analyze the initial tranches of material released by the curation teams, the data is forcing an immediate recalibration of our core computer models of planetary formation. We are learning that rocky planets do not cool and separate in simple, predictable concentric layers like textbook diagrams suggest. They are dynamic, highly asymmetric engines whose life stories can be profoundly altered by their early orbital placement, their proximity to neighboring worlds, and the random, violent interventions of cosmic impacts. The story written into the far side soil is a profound warning against human provincialism. It serves as a reminder that what is obvious, visible, and familiar to us is often just a localized anomaly masking a much larger, more complex structural reality. For millions of years, our ancestors looked up at the familiar face of the moon, assuming that the silver disk was a simple, uniform monument of stone. It took the audacity of modern robotic engineering to cross that threshold of visibility and discover that just out of sight lay a completely different world, a battered, ancient archive of our cosmic birth, quietly waiting in the dark for humanity to finally arrive and read the stones. The transition from macroeconomic geological observation to nanometer-scale laboratory dissection has isolated specific mineral grains that survived the South Pole-Aitken impact event. Inside the ultra-clean preservation environments, technicians use atom probe tomography to strip away layers of atoms from single crystals of plagioclase, ilmenite, and pyroxene retrieved from the core drive. This atomic scale mapping reveals structural anomalies that cannot be detected by remote sensing orbiters. When a mineral grain from the crater is subjected to these ultra-high magnification fields, its internal structure shows a dense network of microfractures, mechanical shock twinning, and high-pressure phase transformations. These features serve as an exact physical pressure gauge. The crystals exhibit structural distortions that occur only under shock pressures exceeding 30 gigapascals. Crucially, this structural deformation is not uniform. It consists of distinct generations of internal lattice damage. An ancient, deep-seated shock pattern generated during the primary basin-forming impact 4 billion years ago is regularly cross-cut, faulted, and sheared by younger microfractures caused by billions of years of smaller, localized meteorite strikes. This structural layering tells us about the cooling environment of the young basin by calculating the orientation and density of these lattice dislocations. Crystallographers have determined that the excavated floor of the basin did not cool rapidly into the vacuum of space. Instead, it remained trapped in a high-temperature state for thousands of years. The basin floor was insulated by a thick, subsurface blanket of fallback, impact melt, and superheated rock vapor that failed to escape the moon's gravity. This prolonged thermal bottleneck allowed the shattered mineral lattices to partially heal, recrystallizing into dense, shock-resistant mineral phases that preserved the structural integrity of the deep basin floor through subsequent eras of cosmic bombardment. Beyond the physical architecture of the mineral grains, the tracking of non-radiogenic stable isotopes within the far-side soil exposes a deep chemical disconnect between the two halves of the moon. When laboratory teams measure the stable isotope ratios of elements like oxygen, silicon, and titanium within the far-side basalts, they find a profile that matches the overall Earth-Moon system, supporting the broad strokes of the giant impact hypothesis. However, when they shift their focus to the isotopic composition of volatile elements like nitrogen and noble gases trapped within the submicroscopic vesicles of the rock, the data deviates significantly from anything seen in the near-side collections. The far-side regolith displays a profound enrichment in heavy nitrogen isotopes relative to light nitrogen. On the near side, this ratio is highly variable and regularly influenced by the Earth's shifting magnetale, which occasionally sprays the visible face with a lighter terrestrial atmospheric signature. The far side's heavy nitrogen profile, completely isolated from this Earth-wind contamination, represents a pure, unedited extraterrestrial signature. This specific isotopic enrichment provides a direct chemical link to a particular class of ancient, volatile-rich primitive asteroids known as enstatite and carbonaceous chondrites. The structural placement of this heavy nitrogen signature, deeply embedded within the pristine volcanic crystals, rather than merely stuck to the outside of the soil grains by the solar wind, proves that these volatile elements were part of the primary ingredients that built the deep far-side mantle. This discovery systematically dismantles the classic dry moon model, proving that significant pockets of primitive, volatile-rich material survived the high-temperature forge of the moon's creation and were held safely inside its stiff, deep interior for billions of years. The stark mineralogical variance of the far side is forcing an immediate reevaluation of how the primary lunar crust solidified from the global magma ocean. For half a century, planetary science taught that the crystallization of the magma ocean was a clean, uniform process that occurred evenly across the entire lunar globe. The buoyant crust was modeled as a simple, concentric shell that floated to the surface uniformly, with the only major variable being its final thickness. The data coming out of the curation teams shows that this global flotation model is a significant oversimplification. The returned far-side highland minerals show distinct differences in their trace element chemistry compared to the near-side counterparts. The far-side crystals possess significantly lower concentrations of incompatible trace elements and display a different europium anomaly profile. This chemical distinction proves that the crystallization of the primordial magma ocean was highly localized and geochemically fragmented. The ocean did not cool as a single, well-mixed bucket of liquid rock. Instead, it was split into vast, isolated chemical domains, driven by deep thermal barriers and complex internal circulation patterns. The far-side crust solidified from a highly primitive, pure domain that was largely cut off from the shifting residual currents that were simultaneously concentrating heat-producing elements like potassium, thorium, and phosphorus on the near side. The thick, pale highlands of the hidden face are not just a thicker version of the near-side hills. They are a chemically distinct lineage of primordial rock that evolved along a separate path from the very moment the magma ocean began to cool. The structural composition of the basaltic fragments returned by the mission provides critical data regarding the kinetics of decompression melting in low-gravity environments. On Earth, volcanism is heavily driven by deep-seated mantle plumes and tectonic plate boundaries that force hot rock upward, causing it to melt as pressure drops. On the Moon, which lacks plate tectonics, volcanism was traditionally viewed as a simple story of internal radioactive heating, magma rising to the surface because the interior was hot enough to melt. The far-side basalts paint a more complex picture. The chemical analysis of these volcanic fragments shows that they are remarkably low in titanium and possess an exceptionally primitive, magnesium-rich profile. This chemistry requires a very deep mantle source that experienced a low degree of partial melting. Crucially, the radiometric ages of these distinct basalt fragments do not form a single, continuous timeline. Instead, they appear as sharp, isolated spikes of volcanic activity that correspond directly with major, localized impact events within the South Pole-Aitken basin. This episodic timeline supports a model where far-side volcanism was entirely driven by impact-induced decompression kinetics. The stiff, cold far-side mantle was physically incapable of generating independent, thermally driven volcanic eruptions. It required a catastrophic external trigger. When a massive asteroid slammed into the far side, it instantly blasted away the insulating crust, creating a sudden drop in the pressure squeezing the deep mantle below. This localized pressure relief caused the solid, hot mantle rock to instantly flash into liquid magma, which then traveled up through the newly formed impact fractures to flood the basin floor. Volcanism on the far side was not an internal choice made by the Moon's engine. It was a series of localized kinetic resurrections forced upon a dying world by the random, violent choices of the solar system's impact history. The physical structure of the loose topsoil brought back provides a masterclass in the dynamics of long-term impact gardening in a vacuum. Every single scoop of the far side regolith is a complex mixture of shattered minerals, microbreccias, and glassy impact debris that has been continuously worked by the space environment for over 4 billion years. Without a protective atmosphere, even the smallest dust particles traveling through interplanetary space hit the lunar surface at speeds exceeding 20 kilometers per second. Under these high-velocity conditions, the top layer of the far side soil experiences continuous mechanical breakdown and recycling. When a micrometeorite strikes the regolith, it creates a highly localized zone of extreme heat and pressure, flash melting a tiny pocket of soil. This liquid silicate spreads through the surrounding dust before cooling rapidly into a complex, branched structure known as an agglutinate. These agglutinates, tiny fragments of mineral grains bound together by a dark, irregular glass matrix, make up over half of the returned far side sample. The structural density and maturity profile of these agglutinates allow scientists to measure the exact rate of impact gardening on a surface that has never been cleaned or reset by major volcanic flows. The far side soil displays an exceptionally high maturity index compared to the younger, volcanically refreshed soils of the near side plains. The far side regolith has been turned over, crushed, and without disturbing the relative boundaries of the separate strata. When this core cylinder was unpackaged in the containment clean rooms, it revealed a multi-tiered structural column that catalogs the depositional history of the crater floor over hundreds of millions of years. The top segment of the core, extending from the surface down to roughly 15 centimeters, is composed almost entirely of highly mature, micropulverized regolith. This layer is characterized by an abundance of agglutinates and nanophase iron particles, indicating prolonged, direct exposure to the space environment and solar wind implantation. The grain size distribution in this upper tier is highly chaotic, with fine dust particles wrapping around larger rock fragments that were thrown into the area by relatively recent, distant cratering impacts. Beneath this modern superficial layer, between 15 and 85 centimeters, the stratigraphy transitions sharply into a coarse, angular impact ejecta blanket. This layer is mostly devoid of agglutinates, indicating it was deposited rapidly in a single, high-energy event rather than built up over millions of years of steady micrometeorite impacts. The mineral fragments within this tier are distinctly anorthositic, showing chemical traits that match the high rim walls of the surrounding crater. This indicates that this entire stratum was created when a sizable asteroid struck the rim of the structure, launching a massive sheet of pulverized wall rock across the basin floor, deeply burying the older surface beneath it. Further down the core sample column, from 85 centimeters to 140 centimeters, the automated drilling system breached an ancient fossilized soil horizon or paleosol. This buried layer represents an old lunar surface that sat directly exposed to the vacuum of space for an extended period billions of years ago, before being sealed away by the overlying ejecta blanket. The recovery of this intact paleosol layer is of immense value for reconstructing the historical changes in space weather across the early solar system. When laboratory researchers analyzed the solar wind gas concentrations trapped within this deep paleosol, they find a profile that reflects a younger, more active sun. The noble gas isotopes, specifically the ratios of various forms of neon embedded within these deep mineral grains, are different from the ratios found in the modern topsoil. This isotopic shift indicates that during the epoch, when this paleosol was at the surface, the solar wind possessed a higher average particle energy and experienced far more frequent flare events than it does today. This deep layer also contains a higher concentration of intact cosmic ray tracks per unit area. These tracks are tiny, microscopic lines of structural damage carved into the mineral crystals by high-speed galactic cosmic rays traveling from deep space. Because the density of these tracks is directly related to the duration of surface exposure, scientists can calculate that this specific paleosol layer sat undisturbed on the far side for approximately 250 million years before it was buried. This long window of stability confirms that the far side experienced extended periods of complete geological calm, punctuated occasionally by massive, catastrophic impact events that completely reshaped the landscape. The lowest section of the core sample, extending from 140 centimeters down to the physical limit of the drill at 2 meters, anchored directly into dense, crystalline mare basalt bedrock. This material represents the primary floor rock of the crater, formed when deep-seated magma reservoirs broke through the fractured crust and pooled inside the basin floor. Unlike the loose soil and fragmented ejecta above it, this bedrock material consists of interlocking crystals of pyroxene, plagioclase, and ilmenite that grew in place as a thick sheet of liquid lava slowly cooled. The microstructural texture of these bedrock basalts shows a distinctly aligned arrangement, where small, elongated crystals of plagioclase are partially or completely enclosed within larger, irregular grains of pyroxene. This interlocking crystal layout indicates a steady, uninterrupted cooling process that occurred beneath an insulating crust of cooling lava. The cooling rate is estimated to have been roughly 1 to 3 degrees Celsius per day, meaning this specific lava flow was several meters thick and took several weeks to fully solidify. The mechanical strength of this bedrock material is exceptionally high, displaying minimal internal microfracturing compared to the loose fragments found in the upper soil layers. This structural integrity proves that while the surface of the far side has been thoroughly pulverized by billions of years of impact gardening, the deeper bedrock layers remain completely intact, preserving the original chemical and physical properties of the volcanic eruptions that resurfaced the basin floor during the Moon's youth. The precise measurement of rare earth element concentrations within the returned far side fragments has exposed a deep structural anomaly in how trace elements partitioned during the crystallization of the lunar mantle. When geochemists plot the concentrations of these elements, the resulting data provides a chemical signature that reflects the exact temperature and pressure conditions of the source region where the magma originally formed. The far side basalts display a highly unusual, flat rare earth element profile that is fundamentally distinct from the curves characteristic of the near side basalts. The far side samples show no major enrichment in the light rare earth elements, such as lanthanum and cerium, and possess a much smaller, less pronounced negative europium anomaly. This subtle europium signature is crucial because specifically charged europium ions are chemically compatible with plagioclase feldspar, meaning that when the primary anorthosite crust floated to the top of the magma ocean, it stripped europium out of the remaining liquid. The lack of a deep europium deficit in the far side volcanic rocks proves that the mantle source region beneath the basin did not experience the same degree of extreme plagioclase extraction as the near-side mantle. This supports a scenario where the flotation of the primary crust on the far side was a rapid, incomplete process that left a higher proportion of primary plagioclase components trapped down within the deep mantle interior. The far side mantle remained geochemically unrefined, retaining a primitive trace element profile that was never subjected to the final, extreme fractionation events that created the highly complex volcanic provinces of the visible face. The analysis of highly siderophile elements, including platinum, palladium, osmium, and iridium within the returned far-side soil grains provides a physical test for the timing of the late veneer delivery to the Earth-Moon system. Siderophile elements are highly iron-loving, meaning that during the primary differentiation of a molten world, these metals are rapidly stripped out of the silicate mantle and pulled downward into the dense metallic core. Any concentration of these elements found in a planet's upper mantle or crust must have been delivered by a late influx of meteorites after the core had finished forming. The far-side basalt fragments reveal a significant deficit in highly siderophile elements compared to the younger volcanic rocks of the near side. This clean, unenriched signature indicates that the deep mantle source region beneath the far side was completely isolated from the late-stage asteroid delivery that peppered the lunar globe after its primary differentiation. The far side mantle represents a pristine, ancient reservoir that preserves the original chemical composition of the Moon immediately following the core formation event, completely unaffected by the later addition of outer space metallic components. This metal-depleted profile provides tight constraints for modeling the mechanical efficiency of core separation. The extreme lack of platinum group elements in these primitive rocks demonstrates that the primary segregation of metal from silicate rock within the early lunar magma ocean was nearly 100% efficient. The dense metallic iron droplets sank through the fluid magma ocean with minimal trapping, ensuring that the primary mantle was thoroughly scrubbed of its siderophile elements before the solidification of the thick far side crust locked the system in place. To map out the exact kinetic timeline of the shock waves that rolled through the basin, laboratory technicians use micro-X-ray diffraction to analyze individual grains of impact melt rock within the collection. This technique allows scientists to measure the internal mechanical strain and crystal lattice distortion within single mineral fragments at a high spatial resolution. The diffraction patterns obtained from the far side melt rocks reveal the presence of a rare, high-pressure polymorph of silica known as stishovite. Stishovite can only form when silica-rich minerals are subjected to sustained shock pressures exceeding 8 to 12 gigapascals and temperatures above 1200 degrees Celsius. The survival of stishovite within these grains is remarkable because it is unstable at standard surface pressures and typically reverts back into common quartz if it cools slowly down from peak temperatures. The presence of intact stishovite crystals within the far side samples proves that the shock wave from the asteroid impact was followed by an exceptionally rapid cooling mechanism, a process known as shock quenching. As the high-pressure shock front rolled through the rock, it instantly transformed the silicate minerals into dense, high-pressure phases. A fraction of a second later, the sudden decompression of the target material caused it to expand and spray outward into the cold vacuum of space, rapidly dropping its temperature before the stishovite had a chance to revert back into its low-pressure form. This finding provides an exact physical metric that allows computational physicists to calibrate the precise shockwave kinematics of massive planetary collisions. The mineral apatite, a calcium phosphate mineral found in trace amounts within the far side basalt fragments, serves as a high-fidelity laboratory indicator for tracking the volatile content of early lunar magmas. Apatite crystals can readily incorporate volatile halogens, such as fluorine, chlorine, and hydroxyl molecules, into their crystal structures, with the relative ratios of these elements reflecting the exact volatile concentrations of the liquid magma from which they grew. When laboratory scientists conduct precise microprobe analyses of the apatite grains from the far side, they discover a volatile partitioning profile that is highly unusual compared to near-side standards. The far side apatites exhibit a remarkable enrichment in chlorine relative to fluorine, along with clear structural signatures of trapped hydroxyl ions. This specific halogen layout is characteristic of highly primitive, deep-seated magmatic systems that never experienced significant degassing. On the near side, The thin crust and widespread volcanic activity allowed ascending magmas to easily erupt onto the surface into a vacuum, causing volatile elements like chlorine and water vapor to rapidly boil off and escape into space before apatite could crystallize. The far side apatites, growing deep beneath the massive protective shield of the thick crust, were held under sustained pressure within deep subsurface intrusions. This pressure prevented the volatile elements from outgassing, forcing them to remain inside the liquid melt, where they were cleanly incorporated into the growing apatite crystals. The recovery of these volatile-rich minerals provides direct proof that the deep interior of the Moon retained a significant portion of its original volatile elements, completely buried and insulated from the vacuum of space. The chemistry of coexisting high-calcium and low-calcium pyroxene crystals within the returned far-side basalt bedrock allows geochemists to apply the principles of pyroxene geothermometry to calculate the exact equilibrium temperatures of the ancient far-side mantle. Because the solubility of calcium within the pyroxene crystal lattice is directly dictated by temperature, measuring the precise distribution of calcium atoms between adjacent grains yields a highly accurate geological thermometer. The application of this geothermometric analysis to the far-side pyroxene pairs indicates that the far-side basalts crystallized at an equilibrium temperature range between 1150 and 1220 degrees Celsius. This narrow thermal window indicates a remarkably stable, well-regulated magmatic environment that cooled steadily without experiencing major thermal fluctuations or sudden secondary heating events. When this temperature data is input into global thermokinetic models of lunar cooling, it reveals that the mantle beneath the far side must have possessed a remarkably low internal heat flux during the epoch of basin formation. This supports the scenario where the far side mantle had already lost the vast majority of its primary internal thermal engine within the first few 100 million years of its existence. The volcanism that occurred inside the basin was operating at the bare minimum thermal threshold required to maintain liquid rock, reinforcing the model that these eruptions were entirely thin, localized events driven by the sudden structural decompression of major impact wounds rather than a broad, healthy, planet-wide volcanic system. The continuous bombardment of solar wind protons and micrometeorites alters the optical and physical properties of the upper lunar regolith over time, a highly complex process known to planetary astronomers as space weathering. By using transmission electron microscopy to inspect the outermost rims of individual soil particles brought back, laboratory researchers can measure the exact kinetics of this surface degradation at the nanometer scale. The far side soil grains are wrapped in complex, amorphous rims of structural damage that extend between 60 and 120 nanometers into the crystal interiors. These rims are completely devoid of an organized crystal lattice, having been entirely transformed into a glassy, disordered state by the continuous implantation of solar wind ions. Dispersed throughout these damaged borders are millions of submicroscopic particles of nanophase metallic iron, ranging from 2 to 30 nanometers in size. The presence and size distribution of this nanophase iron explains why remote sensing observations of the far side have historically been so difficult to interpret. This metallic iron alters the way light reflects off the lunar surface, causing a severe reduction in the overall brightness and a dramatic flattening of the diagnostic mineral absorption bands in the infrared spectrum. By precisely matching the laboratory-measured nanophase iron concentrations of the samples with the remote sensing data collected by orbiting satellites, scientists can establish a highly accurate calibration curve for space weathering kinetics. This calibration allows us to reliably determine the exposure age and mineral composition of other airless, ancient bodies across the solar system solely from their light signatures. To map out the peak shock temperatures achieved during the creation of the South Pole-Aitken basin, researchers utilize micro-Raman spectroscopy to analyze individual feldspar grains within the collection. This technique passes a highly focused laser beam through the sample, measuring the tiny shifts in light frequency caused by the vibrational modes of the internal chemical bonds. This provides a highly sensitive map of the mineral's structural order. The laser spectra obtained from the far side plagioclase crystals reveal that a significant portion of the feldspar has been transformed into a rare, shock-induced amorphous phase known as masculinite. Masculinite is not a true igneous glass. It is a glass-like solid that forms when the crystalline lattice of a feldspar mineral is instantly collapsed by a high-energy shock wave, while completely retaining its original chemical composition and shape. The transformation of plagioclase into masculinite occurs only within a tight pressure window between 25 and 45 gigapascals. The discovery of intact masculinite grains across the floor of the crater allows scientists to construct a precise spatial map of the shockwave intensity that radiated outward from the impact center. The fact that these grains were collapsed into an amorphous state without completely melting indicates that the local peak shock temperatures did not exceed 900 degrees Celsius. This constraint demonstrates that the kinetic energy of the impactor was primarily converted into structural deformation and mechanical displacement rather than uniform, widespread thermal vaporization. This physical baseline allows computational geophysicists to accurately model the original mass and approach velocity of the ancient asteroid that carved out the basin. The concentration and isotopic composition of heavy noble gases, specifically argon, krypton, and xenon, trapped within the deep basalt bedrock fragments of the core sample, provide a chemical timeline for the structural degassing of the lunar core. Because noble gases are chemically inert, they do not bond with mineral lattices and are highly sensitive indicators of deep-seated physical migrations within a planetary body. The far side basalts display a distinct enrichment in primordial xenon isotopes relative to the common atmospheric or solar wind compositions. This specific primordial xenon profile is a match for the ancient chemical signature found within deep-seated mantle plumes on Earth, pointing toward a highly primitive, undegassed source deep within the lower lunar interior. The presence of this unedited primordial gas within the far side volcanic rocks indicates that a fraction of the original volatile elements captured during the initial accretion of the solar system survived the high-temperature forge of the giant impact and remained safely locked inside the moon's deep lower mantle. When this noble gas data is synthesized with computational models of internal mantle circulation, it demonstrates that the sluggish, incomplete mantle overturned beneath the far side acted as an effective structural trap, while the rapid, thorough mantle circulation beneath the near side completely degassed its interior elements into space through widespread surface volcanic eruptions. The cold, high-viscosity far side mantle prevented these primitive gas reservoirs from migrating upward. They remained safely isolated in the deep interior for over 4 billion years until the decompression shock wave from the impact opened up deep mechanical fractures that allowed this ancient, primitive gas to ascend into the shallow crust. The automated engineering instruments on board the lander, including the motor torque sensors on the robotic digging arm and the penetration resistance gauges on the core drill assembly, provided the first direct in-situ measurements of the mechanical properties and load-bearing performance of the far side soil. These structural metrics are critical for designing the foundation systems, structural supports, and heavy excavation equipment for future long-duration outposts. The penetration data reveals that the far side regolith possesses a significantly higher packing density and shear strength at shallow depths compared to the near side landing sites explored by earlier human missions. On the near side, the upper 30 centimeters of soil consists of loose, highly compressible dust that offers minimal resistance to drilling. On the far side, the penetration resistance climbs steeply within the first 10 centimeters of depth, requiring a significantly higher mechanical torque to drive the drill bit forward. This high packing density is a direct result of the extreme angularity and irregular shapes of the far side soil particles. Because the far side regolith has been subjected to continuous long-term impact gardening without the regular flattening additions of smooth volcanic lava flows, The individual grains have developed highly complex interlocking geometries. These irregular fragments wedge tightly against one another under compaction, creating a highly stable, rigid soil matrix that can support significant structural loads without shifting. This unique mechanical stability makes the far side highlands an ideal location for constructing massive, deep-seated scientific installations, such as low-frequency radio telescope dishes or permanent structural habitats, which require a solid foundation that will not settle or deform over time. Embedded within the fine-grained matrix of the returned far-side regolith are trace amounts of microscopic cosmic dust particles that originated entirely outside our solar system, interstellar dust grains that traversed the interstellar void before being captured by the Moon's gravitational field. Because the far side sits completely isolated from the Earth's protective environment and faces directly into the cold expanse of deep space, it acts as an ideal collection plate for gathering this incoming interstellar material over deep time. Mission from the high-stakes environment of the far side, China conducted a complete operational dress rehearsal on the visible face. In November 2020, the Chang'e 5 mission was launched toward a prominent volcanic complex known as Mons Rumker, situated in the vast ocean of storms on the near side. The mission was a flawless display of robotic choreography, involving automated drilling into the surface, scooping loose topsoil, launching an ascent vehicle from the lunar face, and executing a high-speed orbital rendezvous to transfer the cargo into a return capsule. On December 16, 2020, the capsule successfully parachuted onto the frozen grasslands of Inner Mongolia, delivering 731 grams of fresh nearside material. When these samples were distributed to laboratories, they yielded a discovery that fundamentally upended our timeline of lunar evolution. For decades, the dominant paradigm was that the Moon, being a relatively small body with a high surface area-to-volume ratio, had cooled down and lost its internal thermal engine very early in its history. The consensus held that widespread volcanic activity had completely died out by about 3 billion years ago, leaving the Moon geologically dead. But the crystals returned from Mons Rumker told a completely different story. Radiometric dating revealed that these basaltic lavas were only 2 billion years old. Lava had been actively erupting and flowing across the Moon's surface a full billion years later than any model had predicted. This discovery triggered an intense debate. How could a world as small as the Moon sustain enough internal heat to melt rock and drive volcanism so late in its life? Some scientists hypothesized that the mantle beneath the ocean of storms was heavily enriched in radioactive, heat-generating elements, like uranium, thorium, and potassium, which acted as a subterranean blanket. Others argued that the mantle source regions contained high concentrations of trapped water or other volatile compounds, which significantly lowered the melting point of the rock, allowing magma to form even as the Moon's interior cooled down. The Chang'e 5 findings amplified a critical realization. If the well-studied near side could still harbor such monumental geological surprises, our understanding of the completely unsampled far side was likely profoundly flawed. The young lavas of Mons Rumker came from a hemisphere defined by a thin crust and an abundance of heat-producing elements. They could not explain the evolution of the far side, where the crust is systematically thicker, reaching up to 80 kilometers in some regions, and where the surface is ancient and starved of widespread volcanic plains. To comprehend the lunar globe as a complete system, a sample return mission to the hidden face was no longer just desirable. It was an absolute scientific necessity. This set the stage for the historic voyage of Chang'e 6. Launching on May 3, 2024, from the tropical coastline of Hainan Island, the spacecraft carried the heavy burden of attempting what had never been done in human history. To support the mission through the inevitable communication blackout, China had already deployed an upgraded, second-generation relay satellite named QUEQIA-02 in March of that year. Unlike its predecessor, QUEQIA-02 was placed into a highly specialized frozen elliptical orbit designed specifically to maximize the data transmission windows directly over the target zone on the southern far side. On June 1, 2024, the Chang'e 6 lander detached from its orbiting parent and began its autonomous 15-minute descent toward the surface. It was targeting the southern floor of the Apollo crater, a major 537-kilometer-wide structural ring located inside the northeastern quadrant of the giant South Pole-Aitken basin. Because direct human piloting or real-time command intervention from Earth was impossible due to the built-in signal delay through the relay satellite, the lander had to think for itself. Utilizing advanced machine vision, laser altimeters, and optical cameras, the onboard computer analyzed the rushing landscape in real time, instantly identifying hazardous boulders and steep slopes, and making independent trajectory corrections in the final seconds of its powered descent. The spacecraft touched down flawlessly on a gray landscape that had remained largely unaltered for hundreds of millions of years. The operational window on the far side was brief and intense. Within hours of landing, the probe deployed its mechanical systems. A robotic arm repeatedly scooped up the loose, powdery topsoil from the surface. Simultaneously, a specialized core drill bored nearly 2 meters into the compacted subsurface, extracting a pristine vertical profile of the ancient terrain. In total, the mission gathered 1,935 grams of material, just under 2 kilograms of pure, unadulterated far-side regolith. The sample container was hermetically sealed inside a small ascent vehicle parked on top of the landing legs. On June 3rd, the ascent rocket fired, rising silently into the lunar vacuum on a pillar of exhaust. It executed a precise orbital docking with the waiting return module, transferred the capsule, and began the 3-day journey back across the cislunar void. On June 25, 2024, the re-entry capsule plunged into the Earth's atmosphere at 11 kilometers per second, enduring extreme friction before drifting safely down into Inner Mongolia. The return of those 1,935 grams marked the official end of an era of architectural ignorance. Held within a nitrogen-purged, ultra-clean curation facility at the Chinese Academy of Sciences in Beijing, these samples are providing the definitive baseline data needed to test the most fundamental models of planetary differentiation. International teams of scientists from nations including France, Italy, and Pakistan were invited to join Chinese researchers in analyzing these grains, and the early analytical results are fundamentally challenging long-held assumptions. When geochemists isolate and examine the mineral grains from the Apollo crater samples under advanced microscopes, the divergence from the Apollo near-side collections is immediately apparent. The far-side regolith is heavily enriched in magnesium-rich pyroxenes and olivine, matching the predictions of mantle exposure, whereas the classic near-side highland samples are completely dominated by anorthosite, a light, calcium-aluminum silicate mineral. This mineralogical distinction cuts to the very heart of the lunar magma ocean hypothesis, which has served as the foundation of planetary science for half a century. According to this model, shortly after the Moon coalesced from the debris of the Theia collision, its entire outer layer was completely molten, forming a global ocean of magma hundreds of kilometers deep. As this colossal liquid sphere slowly cooled over tens of millions of years, minerals began to crystallize and separate based entirely on their density and melting points. Heavy minerals like olivine and pyroxene crystallized early and sank downward to form the deep mantle. Later, as the remaining liquid became concentrated in aluminum and calcium, the light mineral anorthosite began to crystallize. Because it was less dense than the surrounding magma, it floated to the surface like slag on molten iron, forming a global, primordial crust. The very last dregs of this cooling magma ocean were highly enriched in incompatible elements, atoms whose physical size or electrical charge prevents them from easily fitting into the crystal structures of major minerals. This residual liquid is known by the acronym K-REAP, representing potassium, rare earth elements, and phosphorus. The near side of the Moon is heavily saturated with this creep signature. Because elements like thorium and uranium are radioactive and continuously emit heat, Their concentration on the near side explains why that hemisphere remained hot, fluid, and volcanically active for billions of years, allowing vast floods of basaltic lava to erase the ancient cratering record and create the smooth maria. However, the Chang'e 6 far side samples reveal a profound and systematic depletion in these heat-producing creep elements. This starvation is a massive piece of the planetary puzzle. It proves that the primordial magma ocean did not cool uniformly as a perfect, symmetrical sphere. Some large-scale mechanism pushed the bulk of the residual, heat-producing liquids entirely to one side of the moon, leaving the far side mantle completely deprived of the thermal engine required to generate widespread volcanic activity. Why this profound asymmetry occurred is the subject of intense debate, and the far side rocks are providing the first physical constraints to test mathematical models. One major school of thought suggests that the Earth itself directly shaped this divergence. In the immediate aftermath of the giant impact, the Moon orbited at a small fraction of its current distance. The young Earth was a glowing, superheated hellscape, radiating immense thermal energy into space. Because the Moon became tidally locked almost immediately, its near side was permanently exposed to this blistering radiant heat, while its far side faced the freezing void of deep space. This immense thermal gradient would have fundamentally altered the crystallization rate of the global magma ocean. The far side crust would have cooled, solidified, and grown thick much faster than the near side, creating a massive structural shield that later prevented internal magma from reaching the surface, even as the near side remained a churning, molten soup. An alternative theory, known as the Big Splat hypothesis, relies on a chaotic mechanical intervention rather than gradual thermal differences. This model suggests that the debris disk from the Theia impact actually spawned two separate moons, our current moon, and a second, smaller companion satellite roughly one-third its size. The two bodies would have shared the same orbital plane, slowly drifting until gravitational instabilities caused their paths to inevitably cross. Because they were traveling at similar orbital speeds, the resulting collision was relatively low velocity, a spectacular cosmic pancaking rather than a vaporizing explosion. The smaller moon would have literally flattened itself against the larger body, plastering its entire crustal mass across one hemisphere. This model elegantly explains the extreme thickness of the far side crust. It is quite literally a second moon stacked on top of the first. By conducting precise radiometric dating and measuring the isotopic ratios within the returned Chang'e 6 crystals, laboratory geochemists can read the internal clocks of these rocks to resolve this debate. If the far side crust formed via the gradual, asymmetric cooling of a single magma ocean, the oldest rocks from both hemispheres should yield identical crystallization ages. If the thick far side crust is the result of a secondary accretion event or a massive later collision, the isotopic signatures will reveal a distinct time gap, exposing a multi-stage construction process. Beyond the deep structural history of the Moon, the fine physical structure of the soil particles brought back by Chang'e 6 is providing an unedited archive of the early solar system. Because the far side was never subject to the massive periodic volcanic repaving that cleared the canvas on the near side, its surface has been exposed to the unmitigated fury of space for over 4 billion years. Every single microscopic grain of soil returned from the Apollo crater is a microbreccia, a tiny composite rock made of even smaller fragments welded together by the extreme pressures and temperatures of micrometeorite strikes. This continuous mechanical churning, known as impact gardening, has ground the upper layers of the far side into an incredibly fine, highly irregular powder. Interspersed within this powder are millions of microscopic glass spherules, formed when tiny space rocks collided with the lunar soil, instantly flash-melting the silicate minerals and spraying the liquid droplets into the vacuum, where they cooled into perfect geometric beads before falling back to the surface. These impact glasses act as chemical time capsules of immense scientific value. When a mineral is melted and quenched into glass, it traps volatile compounds and isotopic signatures, that would otherwise escape into space or be altered by subsequent geological processes. By utilizing secondary ion mass spectrometry to analyze the composition of these glass beads, researchers can reconstruct the history and origin of the comets and asteroids that have pelted the Earth-Moon system over the eons. This is a critical chapter in the history of our own planet. Because the Earth is geologically alive, with tectonic plates continuously subducting and destroying the crust, mountains eroding into the oceans, and life actively altering the chemical composition of the environment, almost all physical evidence of the first 500 million years of Earth's existence has been utterly obliterated. We do not possess a single intact rock from the period when life was first attempting to organize itself from complex organic molecules. The far side of the Moon has sat in the silent vacuum of space, flawlessly recording that exact missing epoch. The dense population of craters within the South Pole-Aitken basin represents a physical ledger of the late heavy bombardment, a hypothesized period roughly 3.9 billion years ago, when a massive shift in the orbits of the outer gas giants is thought to have destabilized the asteroid and comet belts, sending a devastating swarm of projectiles screaming into the inner solar system. If this bombardment occurred, it would have blasted the early Earth with enough kinetic energy to repeatedly vaporize the early oceans and sterilize the surface, meaning that life either had to emerge multiple times from scratch or survive exclusively within deep, hydrothermal vents. By precisely dating the impact melts returned by Chang'e 6, scientists can determine if the craters of the far side were formed during a single intense spike of planetary violence, or if they represent a steady, gradual accumulation of impacts over a much longer period. This distinction will fundamentally alter our understanding of the environmental conditions that govern the very origin of life on Earth. The profound scientific yield of these missions is also shifting our perspective on the practical future of space exploration. The reliance on complex autonomous navigation and deep space relay networks like QUEQIAO2 demonstrates that operating on the hidden frontiers of our solar system is no longer a matter of science fiction. The choice of the southern far-side basins as the primary targets for modern space agencies is driven by a powerful combination of unique topography and vital resource availability. Satellites orbiting the Moon have detected massive signatures of hydrogen within the deep, permanently shadowed regions near the lunar poles. Because the Sun never rises above the rims of these deep craters, temperatures hover just a few degrees above absolute zero, creating highly efficient cold traps that have frozen and preserved water ice delivered by comets over billions of years. For a spacefaring species, water ice on the Moon is the ultimate strategic resource. It is not merely a source of hydration for future outposts. It is the fundamental raw material for rocket propellant. By using solar power arrays placed on illuminated crater rims to split water molecules into pure hydrogen and oxygen, future lunar bases can manufacture high-energy rocket fuel directly on the surface. Because the Moon's gravity is only 1/6 that of Earth's, launching a spacecraft from the lunar surface requires a tiny fraction of the energy needed to escape Earth's deep gravitational well. A lunar refueling station would permanently transform the Moon into a gateway to the rest of the solar system, drastically reducing the cost, weight, and complexity of manned missions to Mars and deep space exploration. Furthermore, the far side offers an unparalleled non-physical resource that exists nowhere else in the local space environment: absolute radio silence. The Earth is an incredibly noisy planet, wrapped in a dense, blinding fog of human-made electromagnetic radiation from communications networks, radar systems, and industrial machinery. This radio pollution leaks continuously out into space, blinding our terrestrial radio telescopes and making it extraordinarily difficult to detect the faint, ancient signals traveling from the deep, early universe. The far side of the Moon is completely shielded from this terrestrial din. The bulk of the Moon acts as a massive, 400-kilometer barrier of solid rock that blocks out 100% of human-made radio interference. Deploying a low-frequency radio telescope array across the ancient quiet highlands of the far side would allow astronomers to peer into the cosmic dark ages, the mysterious epoch of cosmic history before the very first stars ignited, when the universe was filled only with a cooling fog of neutral hydrogen gas. This ancient hydrogen emitted a highly specific wavelength of light known as the 21-centimeter line. Over 13 billion years of cosmic expansion, this light has been stretched and redshifted into long, low-frequency radio waves that cannot penetrate the Earth's ionosphere and are completely drowned out by human noise on the near side. Capturing this pristine cosmological signal from the far side would allow us to map the distribution of matter in the infant universe and witness the literal birth of the first stellar structures. As the international scientific community continues to process the data flowing from the curation laboratories, the implications are reshaping our understanding of planetary dynamics. We are discovering that worlds do not cool and differentiate in simple, predictable, concentric shells. They are complex, highly asymmetric engines whose evolution can be profoundly warped by their early orbital environments, their proximity to neighboring worlds, and the chaotic, random interventions of cosmic collisions. The story of the lunar far side is a powerful antidote to human complacency. It stands as a reminder that what is obvious, visible, and familiar is often only a mask for a much deeper, more complex structural reality. For millions of years, our ancestors looked up at the familiar face of the silver disk, assuming it was a simple, uniform monument of stone. It took the audacity of modern robotic engineering to cross that threshold of visibility and discover that just out of sight lay an entirely different world, a battered, ancient archive of our cosmic birth, quietly waiting in the dark for someone to finally arrive and read the stones. The systematic decryption of these physical samples within the high-security curation facilities has transitioned from basic mineral classification into the hyper-precise tracking of isotopic evolution. When planetary geologists isolate individual microcrystals of ilmenite, plagioclase, and apatite from the deeper layers of the core drive, they are not simply looking at pulverized volcanic debris. They are inspecting a structural framework of atoms that solidified under chemical conditions completely alien to the near side. This minute structural variance holds the answers to one of the most intense debates born from the Apollo era, the absolute volatile budget of the infant moon. For 50 years, the dominant consensus maintained that the cataclysmic energy of the impact had entirely desiccated the debris disk, leaving the resulting satellite a completely parched, volatile, depleted world. The far side samples, however, are revealing a far more intricate scenario. Deep within the crystalline structures of these ancient minerals, laboratory teams are identifying unexpected reservoirs of primitive volatile elements, such as hydroxyl molecules, fluorine, and chlorine, trapped at concentrations that suggest the lunar interior preserved an intrinsic moisture budget that managed to survive the high-temperature birth of the Earth-Moon system. To comprehend how a single celestial body can maintain such stark internal chemical and volatile disparities across its two hemispheres, planetary scientists must evaluate the fluid mechanics of the early lunar mantle. In a perfectly symmetrical cooling environment, massive convective currents within a planetary interior act as an efficient blender, churning material over hundreds of millions of years and smoothing out localized chemical anomalies. The synthesis of the mineralogical data with the ultra-high-resolution gravity maps generated by earlier missions indicates that the Moon experienced a radical, planet-wide structural failure known as mantle overturn. As the global magma ocean reached the final stages of its cooling sequence, the remaining liquid trapped beneath the thickening primordial crust began to crystallize specific iron and titanium-rich minerals, most notably ilmenite. These late-stage minerals are remarkably dense, far heavier than the early formed magnesium-rich olivine and pyroxene crystals that had already sunk to the bottom of the magma ocean. This crystallization sequence created a profoundly unstable, top-heavy arrangement, a dense, metallic sheet of iron titanium cumulates, sitting directly on top of a lighter, highly buoyant, lower interior. Under the relentless pull of gravity, this unstable stratification inevitably collapsed. The heavy, superficial ilmenite-bearing layers ruptured and sank downward in massive, planet-wide plumes toward the core mantle boundary, while the lighter, primitive lower mantle material rose upward to displace them. Crucially, the isotopic composition of the basalt fragments retrieved from the Apollo crater proves that this massive mantle overturn did not occur in a uniform, symmetrical fashion. Because the near side was continuously blanketed by the immense radiant heat of the molten Earth and heavily enriched in the radioactive heat-producing elements of the special geological reservoir, the interior mantle beneath the visible face remained fluid and highly convective. This high temperature facilitated a rapid, comprehensive overturn that drew the heat-producing elements even deeper into the near-side interior, creating a persistent subterranean thermal engine that sustained active volcanism for an extra billion years. Beneath the far side, however, the cooling driven by the direct exposure to the freezing sink of deep space created a drastically different dynamic. The far side mantle solidified far more rapidly, creating a highly viscous, stiff interior. The mantle overturn beneath the hidden face was sluggish, structurally impeded, and ultimately stalled before completion. This arrested development locked the primitive, magnesium-rich mantle components in place immediately below the thick far side crust. There they remained trapped in the dark for eons, until the catastrophic South Pole-Aitken impact punched through the protective crustal shield, blasting these deep-seated interior components into visibility. This asymmetric mantle dynamics model receives robust validation from the specific crystallization timelines encoded within the volcanic fragments. If global lunar volcanism had been governed solely by a uniform, planet-wide thermal decline, we would observe a synchronized, global shutdown of volcanic activity across both hemispheres as the interior heat depleted. Instead, the precise radiometric dating of the basalt components from the basin indicates a highly episodic, localized volcanic history that stands in sharp contrast to the vast, self-contained plumbing systems of the near-side plains. The small patches of volcanic mare found within the craters were not fed by a massive, hemisphere-wide reservoir of magma. They are the direct products of localized decompression melting, triggered by external impacts. When a massive asteroid strips away tens of kilometers of solid crustal rock, it instantly unburdens the underlying rock, removing millions of tons of pressure. This sudden drop in pressure abruptly lowers the melting point of the hot mantle material below, causing it to flash instantly into liquid magma without requiring a single degree of additional heat. Consequently, the far side rocks are forcing a massive paradigm shift in how we interpret the volcanic lifespan of small planetary bodies. Volcanism is not merely an internal countdown clock governed by a world's age and initial thermal budget. It welded back together millions of times over its lifespan. Embedded within these microbreccias are tiny nanoscale particles of metallic iron, created when solar wind hydrogen chemically reduces the iron oxides in the lunar soil during impact melting. This nanophase iron alters the optical properties of the regolith, darkening its appearance and dampening its spectral signatures, providing a physical metric that allows astronomers to accurately calibrate their remote sensing data for other airless, ancient bodies across the cosmos. The microscopic glass spherules distributed through the regolith are proving to be some of the most geochemically valuable components of the entire collection. These perfect geometric beads, ranging from a few micrometers to several millimeters in size, were formed when larger meteorite impacts launched plumes of molten rock high into the lunar vacuum. As these liquid droplets fell back toward the surface, they cooled rapidly in midair, locking their chemical components into a stable, non-crystalline structure. Because glass lacks the organized crystalline lattice of minerals, it does not selectively reject or accept specific atoms based on their size or charge during solidification. It acts as an unbiased chemical sponge, freezing a perfect, unedited snapshot of the target terrain at the exact microsecond of the impact event. By using advanced laser mass spectrometry to analyze the core of these individual glass spherules, laboratory teams can identify the exact elemental makeup of the ancient far-side crust before it was pulverized by billions of years of bombardment. Furthermore, these glass beads act as highly secure storage units for volatile gases. In a standard mineral crystal, volatile compounds like sulfur, water, and noble gases easily escape through the lattice boundaries over deep time. In a continuous glass matrix, these volatile elements are trapped in place, completely isolated from the vacuum of space. Extracting these gases in the laboratory allows scientists to calculate the exact composition of the ancient lunar atmosphere, a transient, thin envelope of rock vapor and volcanic outgassing that briefly wrapped around the moon during its early active epochs, before being swept away by the solar wind. The deep population of impact craters within the basin provides the definitive record needed to evaluate the late heavy bombardment hypothesis. This fundamental model suggests that roughly 3.9 billion years ago, a major orbital disruption among the outer gas giants sent a devastating wave of asteroids and comets hurtling into the inner solar system, pummeling the early Earth, Moon, and Mars in a brief, intense spike of cosmic violence. On Earth, the physical proof of this formative era has been completely destroyed by billions of years of plate tectonics and weather erosion. The far side of the moon, protected by its thick crust and lack of massive volcanic resurfacing, holds the only complete physical record of this ancient bombardment. Prior to recent missions, scientists had to rely entirely on samples from the near side, which were heavily contaminated by impact debris thrown from a single, massive near-side event that created the Imbrium Basin. This localized debris created a false peak in the data, leading many models to conclude that the entire solar system experienced a sharp spike in impacts at that specific time. The precise radiometric dating of the impact melt rocks brought back from the far side is systematically testing this model. If the late heavy bombardment was a real solar system-wide event, the far side impact melts should display a tight cluster of crystallization ages right around 3.9 billion years. If, however, the ages of these far side impact rocks are distributed evenly across a longer timeline, stretching from over 4 billion years ago, it proves that the craters were built up gradually over a long period of steady bombardment. This distinction is vital for understanding early Earth history. A sharp, intense spike of violence would have completely sterilized our planet's surface, resetting the clock for the origin of life. A gradual, steady accumulation of impacts would have left stable environmental pockets, allowing early organic molecules to steadily organize and survive within deep oceanic trenches or stable crustal environments. The operational validation of these missions highlights a major shift in the technological landscape of deep space exploration. The absolute necessity of using advanced relay networks proves that exploring the hidden territories of our solar system requires moving past simple line-of-sight tracking. A halo orbit around the balance point behind the moon, or a frozen elliptical lunar orbit, is an intricate gravitational balancing act. This specific space location is located roughly 65,000 kilometers beyond the far side of the moon, where the competing gravitational pulls of the Earth and moon balance out. However, this equilibrium is highly unstable. It functions as a gravitational ridge. A spacecraft parked there requires constant, ultra-precise orbital corrections and thruster firings to prevent it from sliding down the gravitational slope and drifting out into interplanetary space. Managing this complex orbital path while simultaneously maintaining a high-bandwidth, continuous data stream through thousands of kilometers of solid lunar rock requires automated ground tracking systems and autonomous onboard navigation routines that were completely impossible during the 20th century. The relay satellites utilized upgraded, highly eccentric frozen orbits that kept them positioned over the southern far side for extended periods, providing stable communication windows for the lander's robotic arm and drill. This dedicated infrastructure has laid the technical foundation for a permanent communication network, making the far side accessible for future long-duration exploration arrays and permanent scientific outposts. The successful touchdown of the lander inside the crater was a major milestone for autonomous robotic engineering. Because the Moon blocks all direct radio signals between Earth and the far side, the critical 15-minute powered descent window had to be managed entirely by the spacecraft's onboard computer. The time delay introduced by routing telemetry through the relay satellite meant that ground controllers could only watch the descent. They had no way to intervene in real time if something went wrong. To safely navigate down to an unmapped, crater-strewn landscape, the lander used an advanced machine vision system driven by real-time laser altimetry and optical hazard detection algorithms. As the main braking rocket fired, slowing the probe's descent, onboard cameras snapped continuous images of the approaching surface. The system instantly processed these visual fields, comparing them to preloaded topographic maps to calculate the precise altitude, descent velocity, and horizontal drift. During the final, critical hover phase, at an altitude of roughly 100 meters, the lander paused its descent, using its laser scanners to build a highly detailed, three-dimensional topographic map of the immediate landing zone. The computer analyzed this data within seconds, identifying dangerous boulders, hidden microcraters, and steep slopes that could tip the spacecraft over upon touchdown. After selecting a safe, flat pocket of soil, the system executed autonomous lateral corrections before cutting the main engine and settling onto its 4 shock-absorbing legs. This level of robotic independence marks a new era in space exploration, proving that machines can safely explore the most hazardous, isolated environments in the solar system without requiring a human pilot or constant hand-holding from Earth. The strategic focus directed toward the lunar South Pole and the deep basins of the far side by global space agencies is driven by a practical calculation of geography and resource distribution. Because the Moon's axis of rotation is tilted at a mere 1.5 degrees relative to its orbital plane, the Sun never climbs high into the sky at the lunar poles. It crawls along the horizon, casting immense shadows inside deep, low-lying impact structures that have remained dark for billions of years. These permanently shadowed regions function as massive, ultra-cold traps. With temperatures hovering around 40 Kelvin, just 40 degrees above absolute zero, they are among the coldest known environments in the entire solar system. When volatile-rich comets collide with the Moon, a portion of the vaporized water migrates through the vacuum until it lands inside these dark polar traps. Once inside, the water molecules freeze instantly into the ultra-cold soil, locked in place for geological ages. For a spacefaring species, this frozen water ice is an invaluable resource. It is the raw material needed to build a sustainable logistical infrastructure in deep space. By setting up solar power arrays on high, permanently illuminated crater rims, future outposts can generate a steady stream of electricity to power robotic mining equipment down inside the dark zones. This harvested ice can then be processed through high-efficiency electrolysis systems, splitting the water molecules into pure hydrogen and oxygen. This is the exact chemical mixture used to produce high-energy liquid rocket propellant. Because the Moon's mass is significantly less than Earth's, its gravitational pull is only 1/6 as strong. Escaping the Moon's gravity requires a tiny fraction of the energy needed to break free from Earth's deep gravitational well. Building a commercial refueling station on the lunar surface would completely change the economics of space travel. Spacecraft would no longer need to carry all their heavy fuel from Earth's surface, allowing them to launch with significantly larger scientific or commercial payloads. The far side and its polar basins are positioned to become the premier refueling depot of the inner solar system, transforming our satellite from an object of remote study into the essential launching pad for long-duration human missions to Mars, the asteroid belt, and beyond. While the polar regions hold the physical resources needed for fuel production, the far side of the Moon possesses an equally valuable, non-physical resource that exists nowhere else in our region of space: complete electromagnetic isolation. The Earth is an incredibly noisy planet, wrapped in a dense, chaotic blanket of human-made electromagnetic radiation. Every television broadcast, cellular network, radar system, and industrial radio array leaks signals out into space, creating a blinding fog of radio frequency interference. This global noise pollution severely limits our ability to study the universe. Terrestrial radio telescopes are continuously drowned out by this local background din, making it incredibly difficult to detect the faint, ancient electromagnetic signals traveling from deep space. The far side of the Moon is the only location within human reach that is completely protected from this human-made interference. The Moon's solid mass functions as an absolute barrier of rock that completely absorbs all incoming radio signals from Earth. This radio shadow provides an unparalleled location for deep space astronomy. Setting up a low-frequency radio telescope array across the quiet highlands of the far side would allow astrophysicists to peer directly into the cosmic dark ages, the critical epoch of universal history before the very first stars ignited. During this era, the infant universe was filled only with a cooling, expanding cloud of neutral hydrogen gas. This gas emitted a highly specific wavelength of light, known as the 21-centimeter line. Over 13 billion years of cosmic expansion, this ancient signal has been stretched into long, low-frequency radio waves that cannot penetrate the Earth's ionosphere and are completely drowned out by human noise on the near side. Capturing this pristine cosmological signal from the quiet isolation of the far side would allow us to map the precise distribution of matter in the infant universe, offering an unedited look at the literal birth of the first stellar structures and galaxies. The ongoing analysis of the material brought back is driving a fundamental shift in how we interpret the evolution of small planetary bodies. For decades, planetary science relied on a simple, uniform model of planetary cooling. It was assumed that small worlds like the Moon or the asteroid Vesta cooled in regular, concentric shells, with their internal volcanic lifespans dictated entirely by their size and initial thermal budget. The far side samples systematically dismantle this neat, predictable picture. They prove that planets can develop deep, long-lasting structural and chemical asymmetries that persist for billions of years. The stark differences in crustal thickness, volatile concentration, and volcanic activity between the two halves of the Moon show that a world's evolution is heavily shaped by its early orbital environment, its close gravitational interactions with neighboring planets, and the chaotic history of cosmic impacts. The gray soil retrieved from the basin is a profound warning against scientific provincialism. It proves that what is obvious, visible, and familiar to us from our vantage point on Earth is often just a localized anomaly masking a much larger, more complex structural reality. For millions of years, humans looked up at the familiar face of the Moon and assumed they understood the silver disk. It took the persistence of modern robotic engineering to cross that threshold of visibility, venture into the hidden dark, and discover an entirely different world, a battered ancient archive of our cosmic birth, quietly waiting for humanity to finally arrive, pick up the stones, and read the baseline history of our solar system. The retrieval process employed did not merely gather horizontal surface dust, it preserved the structural layering of the subsurface. The core drill assembly used a non-rotary continuous sleeve extraction system designed to pull a 2-meter vertical segment of the lunar interior